Alright, welcome back to particle physics and the Standard Model. This is lecture 44, and in the last class, as you can see, we obtained an expression for neutrino oscillation probability, or the probability for mass induced flavor change after the neutrino flavor eigenstate propagates, right, for a two flavor system. So we obtained this as the expression for retrieving an electron neutrino back as an electron neutrino after it propagates, okay. And as expected, it depends on the mixing angle given to us by nature, but also on the difference in the square of the masses in the mass eigenstate, okay. But it also depends on the length that was travelled by the neutrino, which is also known as the baseline, alright. And finally, it depends on the energy of the neutrino in that you get from the source, right. And it had all the correct properties. We saw that there was also some symmetry here, where if you want the probability for retrieving a muon neutrino as a muon neutrino, that is the same as PEE, and since probability add up to 1, PE mu was 1 minus PEE and P mu E was 1 minus P mu mu, okay. Then I wrote down the expression for three flavor oscillations, because that is really the correct formula in the real world. The two flavor oscillation picture is a toy model for us to understand what is going on. In most cases it still works, you can still do away with the two flavor model, but to be very realistic you need a three flavor model, and I asked you to go derive it yourself, right. And you can check this formula against the two flavor formula by setting the appropriate PMNS elements to 0, okay. And then we saw the notion of an oscillation length, which one can do by plotting the probability. You do not even have to actually plot it, it helps to visualize the probability of a muon neutrino being retrieved as an electron neutrino or vice versa, which is this. And we saw that the amplitudes of these probability oscillations is given to you by nature, that is sin square 2 theta. There is nothing you can do about it, theta is fixed by nature in the Lagrangian, right. But the point in the baseline, right, the baseline that you can set for an experiment at which you can measure the maximum conversion from one flavor to another, that is in your hands, right. So if you choose that to be around the oscillation length, or rather half the oscillation length, or half integer values of the oscillation length, that is exactly where you get sin square pi by 2 in the second sin square here, and that gives you the maximum probability you are at the actual amplitude of this conversion. So if you want to make good measurements of this delta m square in particular, then choose your neutrino energy wisely, choose your baseline wisely, and make your measurement, okay. And we saw that this is exactly how physicists did measure the delta m squared between the first and the second and the first and the third eigenstates, okay. So and these are the values as I have written them down here. So what do we mean by first and the second, first and the third? It necessarily means, by convention, we are taking we say that the 1 is the lightest one, okay, 2 is the second lightest, and third is the third lightest, the heaviest, okay. But that is the usual convention, okay, or the usual ordering, okay. In this case there is a technical term for it, it is a normal ordering, but pretty soon we will compare this with another ordering, okay, which is called inverted ordering, where we will not have this, okay. So if this sounds a bit cryptic, hold on for a second, we will see exactly how to think of the two orderings. Okay, once we see some more about oscillations, measurements of the delta m squareds. Okay. Okay, so I was saying at the end of last class that the delta m12 squared came from measurements of solar neutrinos and the delta m13 squared came from the measurements of atmospheric neutrinos. Okay. Among these, atmospheric neutrinos are easier to understand first, so let us start with that. Okay. So, here is what people did to measure delta m 13 squared. See, I am going to draw the earth, okay, and what I have drawn, let us call that the edge of the atmosphere, okay, because it is in blue. So, I started drawing in blue, might as well call that the edge of the atmosphere, and I am going to draw the crust of the earth in purple. Okay, this picture is obviously not to scale. All right. So, this atmosphere is around 15 kilometers thick. Okay, many people define the boundary of the atmosphere at different points. Let us just call it 15 kilometers. What is the radius of the earth? That is around 6,400 kilometers, right. So, this plus inside a circle, that is the historic, that is the conventional symbol for earth, right. Okay. Now, that would mean that a typical chord length in the earth is how much? Up to the order of magnitude. It is about 1,000 kilometers, right. That is the order of magnitude. Okay. So, why are we saying all this? Because the earth's atmosphere, if you had not heard it before, is bombarded by cosmic rays. Surely you heard of cosmic rays, right? And cosmic rays are made of what? Mainly protons. There are some electrons, some heavy nuclei, all sorts of things, antiprotons, anti-helium, but by and large cosmic rays are made of protons. Okay, they come from all over the galaxy to come and rain down on the earth. They are raining down on you right now. Okay, it is a very interesting topic in its own right. But when they come in, what do? The protons, the cosmic ray protons, let me just call it PCR. Okay, they hit the nuclei in the atmosphere, all right, and breaks the nuclei into basically more protons, neutrons, pions and so on. Okay. So, what you actually do is you break them into quarks and gluons and then they immediately confine to all these composite states. Okay. Alright. So, let me just give this a name so you do not get confused, nuclei in the atmosphere. Okay. So, you have to imagine now the atmosphere as a fog, a cloud of pions and neutrons and protons coming from cosmic rays breaking all the nuclei apart. Okay, that is literally what is going on. Okay. Now, most of the shower, this is called a QCD shower. Okay, this is a primary shower basically, okay, or a hadron shower. Most of this is made of pions. Okay. And the pions, as soon as they are produced, the charged pions in particular What do they decay into? Remember when we talked about CP violation and even just parity violation and all that, we wrote down a decay channel for pi, the charge pion, right? What was that? It is a muon. The pi plus goes to a mu plus and the pi minus goes to mu minus, correct? And if you produce a mu plus, you get an antineutrino, which is a muon flavor. If you produce mu minus, you get just a neutrino, again of a muon flavor, correct? Now further, the muon itself decays, right? So a mu plus would decay to an E minus, a mu plus would decay to an E plus and a mu minus to an E minus. So it gives me basically, this is another weak decay. I get this. So you can conserve all the lepton numbers and everything correctly, charge and lepton number and everything, okay. The key here is to count the flavors, okay. At the end of the day, if I make a pion, right, how many electron neutrinos do I get with respect to muon neutrinos? You expect that the number of muon neutrinos, whatever, it's a neutrino or antineutrino, doesn't matter for this discussion. What should this be? This is 2, right? You see here, right? So 1, 2 for each electron antineutrino, okay. Okay, now that's what you expect, but when people try to look for, try to count the actual number of electron neutrinos and muon neutrinos at the right energy range, okay, what do they find? What was measured, okay, at detectors was that this ratio was around 0.5 to 1 actually, depending on your energy, the direction in which you are measuring and all that, but it was never 2. That's the main thing here, much smaller than 2, at least half of 2, sorry, at most half of 2, okay. So why could this be? Can you pause the video and answer? The answer is in everything that we've been doing so far, okay. Yeah, it's very simple. It happened because muon neutrinos oscillated into electron neutrinos, okay, but that's not the entire answer, because electron neutrinos also oscillated to muon neutrinos, right? So shouldn't you restore them? Well, you also had muon neutrinos oscillating to tauan neutrinos, okay, and that also oscillated back, and it so turns out that the electron neutrino to tauan neutrino oscillation is pretty suppressed, okay. So the net effect is that the muon neutrinos are depleted, okay. So okay, that's the first part here, okay. Now let us work out what would be a good oscillation length to measure this conversion, okay. So what do? We go back to this equation, right, and we ask if, in fact we can ask a reverse question, okay. If this is the oscillation length, okay, then would I be able to measure a delta m square over here, Okay, see, all I've done is I've just rewritten this. I've got rid of factors of 4 over pi. I'm just taking that as 1. Okay, and what is the oscillation length here? That's about 1000 kilometers. Okay, so basically we are asking whether this 1000 kilometers, right, the typical chord length of muon neutrinos and electron neutrinos being produced here, passing through the rock of the earth, the core and the mantle and the crust, getting to the other side where physicists are waiting to measure these neutrinos, right. We are asking whether that typical chord length is also a good oscillation length. If so, we will see the probability of conversion the most, and in that process we can also measure delta m squared. Okay, is that clear? It all comes down to maximizing the probability of conversion that we can measure. Okay, so we have to choose L oscillation and energy accordingly. Okay, so let's see if this really works out. Now that would mean I need to tell you what the energy of the neutrinos should be, correct? That is an input that comes from cosmic ray physics. Okay, so the energy of protons coming from cosmic rays, right, peaks at around a GeV. Okay, and since it's the, when the proton comes in and hits the nucleus, you produce the pions and everything. At the end of the day, all the energy, most of the energy carried by the neutrino comes from the proton at the end of the day that you started out with, right. So that would mean we can take the energy of the neutrinos to be more or less a GeV. Okay, now what else should I be doing? I know that this is 1000 kilometers, right, but better to express everything in terms of electron volt, correct? So I am gonna do just that. So I am gonna give you how to do the conversion. Again, this is very easy to check, go check this yourself. Go back to the lecture on how natural units are derived, and you will find this is the conversion between electron volt and centimeters. Okay, or said differently, a centimeter is 5 times 10 power 4 inverse electron volt. And what's 1000 kilometers? How many centimeters is that? 1 kilometer is 10 power 5, right? Centimeters. So this is 10 power 8 centimeters. So that is what? Basically 5 times 10 power 12 inverse electron volt. Okay. So if this is the correct baseline, then we can check whether then we can check whether the delta m square we are getting from this estimate is indeed the correct one. Okay, so that's what I'm gonna do. This is now E nu over L oscillation is now GeV over 5 times 10 power 12 inverse electron volt. What is a GeV? 10 power 9, right? Electron volt. So that would give me 2 times 10 power minus 4 electron volt square. Did we get the correct value? Not really. See, what we got was 2 times 10 power minus 3 electron volt square, right? So let me write that actually what you measured here, ATM is for atmosphere, right? Atmospheric neutrinos. What you actually measured was 2 times 10 power minus 3 electron volt squared. But you know what, I am going to say this is good enough. Why? We are doing a very simple modeling here. and we are still within a factor of 10, right. The reason we are off is that this is a better fit to all the data. We are just, we are only taking one chord length here, and then we are assuming there is no real spectrum for the cosmic rays. All the cosmic rays are at 1 GeV and so on, right. But if you were to account for all those things, not only that, if you were to account for all the data that includes the angular spectrum, okay, and something called matter effects, which we are going to see right away next, okay, then you get 2 times 10 power minus 3 electron volt squared. So what do you mean by angular spectrum? You can literally, your detector, if you have directionality capabilities, which most detectors do, right, you can tell how many neutrinos came from this direction, how many neutrinos came from this direction, how many came from this direction. So you can measure the probability conversion for each direction also, okay, and every direction corresponds to a different baseline, right, a different chord length through the earth, correct. So putting all that data also into the mix will pinpoint the correct value of delta m that you measure, delta m squared that you measure from the atmosphere, okay. So that is what this is, but our estimate already gives an answer that is good enough, okay. So this shows a real world application of the probability conversion formula, okay. Now let us see how the solar neutrinos are measured, but along the way it would be useful to check one other case of oscillations, okay. So I am going to sort of summarize what we did and then use that to check these other effects, okay. So the summary is, the conditions for good measurement of neutrino oscillations, okay. So once again let me write down the 2 flavor system probability formula: sine square pi L over L oscillation. Firstly, this should not be too small, provided by nature, and next L should not be too short, right, compared to the oscillation length, and this is fixed by humans, correct. So intuitively from this picture you can see that, right. If I take a very small L here, then I have not given it enough time to oscillate. That is what it means, that you can't, if you put the baseline too short compared to the oscillation length in the problem, then you are not going to see much of an effect, okay. So we can now write, it is useful to write the argument of the sign there, the pi L over L oscillation, right, inside here, that is about, I am going to normalize the L to a kilometer and delta m squared. So remember the L oscillation contains E and delta m squared over here, right. So all I am doing is rewrite this, I am normalizing it normalizing each quantity to a certain number so that we can immediately see what baseline we should choose for a given energy. Okay. So, if I have an GeV energy, then if delta m squared is EV squared, it is not obviously, then the baseline I have to choose is a kilometer. Okay. All I have done is do some unit conversions, the sort of thing that we did over here. Okay. So, that is why if I picked L as 1000 kilometers for GeV neutrinos, I get delta m squared, that is of the order of 10 power minus 3 electron volt squared. Okay. Now, this may be so, but in many situations, okay, you can also get the baseline much larger than the oscillation length. Okay. So, again let us go back to this picture, that is the oscillation length, but it may be that the neutrinos are produced very far away, so that your baseline is actually millions or billions of oscillation lengths. So, what situations are we talking about here? This would be, for instance, neutrinos from supernovae, okay, or neutrinos from extragalactic sources like blazars, and so on and so forth. Okay. The oscillation length might be just a few hundred kilometers or whatever, or 1000 kilometers, but these are light years away, not even light years, I mean mega light years away, some of these, right. So, how would you think of it then? What would you put into the sine square pi L oscillation? What is the value of that? Notice that at this point, this quantity inside, right, pi L over L oscillation, this sine is basically a very fast oscillating function, correct. So, what value of L will you really put there? Because it's oscillating that fast, will you put half the oscillation, I mean half integer value for the oscillation length or integer value for the oscillation length? It goes from 0 to 1 so quickly, right. So, in these cases, what you would do is take the average of the sine square, okay, over a cycle, over many cycles if you want. And remember what this is from your high school calculus, go back and get this average. The average of sine is what exactly over one cycle? The average of sine is 0, right. Half the time it spends its time being positive, half the time negative, and then for every positive value you get the exact same negative value. But for sine square, it is half. Okay. And in this case, the probability, go back here and see, for converting from one flavor to another is just half sine square 2 theta. Okay. So, to give this words, this is the fast oscillation regime, and the picture here to have is, the oscillations are very fast compared to the baseline length. So, this is the oscillation length, okay. And of course, the amplitude is given by, let me draw that in green. So, the amplitude is given by sine square 2 theta, but of course, that is just the amplitude, the probability is given by half of that. Okay. Okay. So, this is one other physical regime, but of course it does not help us get the delta m or anything like that. Okay. The other delta m that we got, as I promised before, comes from solar neutrinos. Okay. And I am going to wrap up the lecture by introducing a problem. I am just going to state the problem called the solar neutrino problem. Okay. This was a problem that persisted since the mid 60s all the way to 2001 actually. Okay. So, I am just going to state the problem and end the lecture. The problem was that the number of neutrinos that were supposed to be produced in the sun were not seen in the earth, and in particular we are talking about electron neutrinos that were produced in the sun were not seen on earth. The answer is, of course, they oscillated away just like we saw in atmospheric neutrinos, but now there is a twist. Okay. We will have to quantify how much we did not see, and we will see how this helped us measure the other delta m squared. Alright, so I will stop here. We will explore this in the next lecture. Thank you.